Hello, my name is Tom Fay, and today's video presentation will describe the restoration to running condition of a vintage Bantam 3.5 twin engine. This is a two-cycle spark ignition engine, and although the engine appeared to be in decent shape as shown here, the internal components required some effort to produce a running engine. The Bantam 3.5 is an all-magnesium two-stroke engine that displaces 3.5 cubic inches, or 57 cc's, and produces 3.5 horsepower. The Bantam 3.5 was initially built in 1943 to the 1945 time period for experimental projects as well as to power 1/8 and 1/10 scale radio-controlled flying models of Convair aircraft, particularly flying boats, where the models were used to optimize the aerodynamic and hydrodynamic performance of the boat hulls. The Convair models were initially powered by the Olsen twin engine, shown on the right, also known as the P4Y, which displaced 2.8 cubic inches and produced up to 2.5 horsepower. These two beautifully restored engines are in the collection of the Miniature Engineering and Craftsmanship Museum located in Carlsbad, California. The Bantam 3.5 twin was described in the January newsletter of the Model Engine Collectors Association in 1968. The engine was designed by Ben Shereshaw, and the dynamic compression ratio, or the true compression ratio of this two-cycle engine, is 8.7 to 1. Here is a newspaper clipping as well as two photographs of the model XP5Y-1 in action. Concurrent with the use of the Bantam twin in the Convair flying models, the Bantam twin was also considered for use in an experimental tethered coaxial helicopter which would be used by downed pilots to raise a rescue antenna. The project was terminated in its infancy. The Bantam twin was also designated to power a quarter-scale, four-engine radio-controlled B-17 model for Spartan aircraft for use as a glider tug for subscale experimental aircraft. This project was never completed. However, starting in 1959, Republic Aviation used the Bantam twin to power their Bikini subscale reconnaissance drone under development for the U.S. Marines. After 7 years of testing, the Marines acquired at least 20 aircraft for evaluation purposes, including a brief deployment to Vietnam in the 1966-1967 time frame. The aircraft had a wingspan of 8 feet, weighed 60 pounds, had an endurance of 30 minutes, and carried a 70mm automatic camera with a 80 exposure roll of film. The aircraft was guided from the ground by radar, launched by catapult, and recovered by parachute. The Bikini had a very high failure rate in the field. Based on this history, certainly 50 and perhaps up to 100 Bantam 3.5 twin engines may have been produced. It is presently unclear which surviving engines belong to which era. In 2024, I was able to acquire a mostly complete Bantam 3.5, plus 3 additional partially complete engines to help the restoration of at least one to running condition. The only markings I could find on any of the Bantam 3.5s were AALA or 4ALA stamped into the magnesium rear cover, and also on 2 engines, the number 4 or the number 2, which was stamped into the crankcases. The structural components of the Bantam 3.5 are made of magnesium. The cylinders are steel and the cylinder heads are aluminum. To disassemble the nose case, a pair of long bolts were adapted to act as pry bars for the nose cover. With the cover removed, the shielded New Departure 7501 ball bearings are revealed. Heating the nose case to 325 degrees Fahrenheit provides differential expansion between the steel ball bearing and the magnesium case, and this allows the bearings to be removed. The steel cylinder is secured to the crankcase with 4 cap screws. Once removed, the cylinder can be pulled off of the piston. The pistons were shown to be heavily carboned, very well used, and the wrist pins, which were supposed to be free-floating, had to be pried out of their bores with a C-clamp. Some of the cylinders proved difficult to slide off the piston, and this was due to dimpling of the rather thin steel skirt as shown in these photographs. These engines have been assembled and disassembled several times over their lifespan. The rear cover is secured to the crankcase with 7 832 size cap screws. One of these cap screws is shorter than the other 6, and it needs to be installed in a specific location in the crankcase. If not, the screw end protrudes into the lower cylinder bore, dimpling the cylinder liner. On the left is what a healthy cylinder looks like. It has 4 exhaust ports and 3 transfer ports. You can see in the right-hand panel the dimple in the center of the photograph with an arrow showing a tear in the cylinder liner, as well as witness marks in the circle, and these are on the piston, caused by the piston going up and down and rubbing on that dimple. The aluminum connecting rods in the Bantam 3.5 have sleeve bearings both in the little end and the big end. The little end is a single-piece sleeve bearing, while the big end is a cap held on by 2 1/64 screws, as well as a 2-piece sleeve bearing that's pinned in place into the connecting rod. Of note on the left is that these sleeve pieces do not fit tightly together. There's an intentional gap left, and I believe that is to allow oil in to lubricate the bearing. One of the connecting rods in the parts case was missing the pins that held the bearing shells into the cap or the connecting rod. Shown here are those 4 pieces, as well as the 2 Philister head 1/64 cap screws. These cap screws proved to be an issue in these engines. This photograph shows one of the cap screws sitting on top of the crown of a Bantam 3.5 piston. Inside of the 3 circles can be seen the imprints of a cap screw that had worked its way loose from the connecting rod and made its way up to the top of the cylinder. On the right-hand panel, you can see the imprint of the fragment into the cylinder head. When these cap screws came loose, they would scar the interior of the crankcase, shown in the right-hand circle, whereas that relief should be smooth, as shown in the left-hand circle. The crankcase did have a pressure tap, shown in the left-hand picture in the center of the photograph, and the right-hand photograph shows the pressure tap in place. 2-stroke engines get their lubrication from oil included in the fuel, which goes through the crankcase. In the rear case on the left, you can see damage to the intake lip, and you can also see a relief cut into the bronze sleeve bearing, and this relief helps sequester oil to lubricate the tail end of the crankshaft. In the rear case on the right, an improvement has been made where the dowel rod shows a port has been drilled between the face where the rotary valve seats into the bearing itself, and this was a much better way to provide oil to the tail bearing. These photographs provide some detail showing that the cylinder head has been removed, the thin copper gasket which seals the head to the cylinder, as well as the ports and the well-run nature of this engine. This photograph shows the front and rear of the rotary valve for the Bantam 3.5, as well as the spring washer, which is a spring-loaded wavy type washer which applies pressure to the rotary valve to keep it seated up firmly against the rear cover there is a 97-degree cutout for the intake. The Bantam 3.5 is a simultaneously firing engine, meaning that both pistons reach top dead center at the same time and the spark plugs on each side fire at the same time as well. This is accomplished by a dual coil. What happens is the points are closed, which energizes the dual coil, and then the rubbing block comes up over the ramp, opens the points, and that will fire the spark plugs. This is the nickel steel crankshaft for the Bantam 3.5. It's about 8 inches long, it weighs almost 9 ounces, it has a 5-degree taper on the propeller shaft, and a keyway. The Bantam 3.5 has a distinctive tall carburetor that's about 1 inch in diameter. Fuel mixture is controlled by a typical needle valve, and this needle valve assembly feeds a chamber inside of the two-piece carburetor. The photograph on the left is a view down the carburetor showing the annular gap where fuel is admitted into the flowing airstream. The right-hand panel shows the two-piece construction of the carburetor, and there is a gap between these two pieces that provides the annulus for the fuel to enter into the carburetor. This particular carburetor had no throttle or choke. There is at least one surviving Bantam twin that has a throttle carburetor, and that's shown in the center panel. The carburetor on the right has the holes for a throttle assembly, which appears to be missing. After selecting the best components to build up the running Bantam 3.5, the components were cleaned, and then the magnesium components, the front cover, the rear cover, and the crankcase, were fine bead blasted, wiped with lacquer thinner, and then sprayed with shellac. I chose shellac because it's highly durable with the fuels I was going to use in this engine, and it leaves a really nice titanium-colored patina to the magnesium. Gaskets were cut from brown craft paper. In preparation for final assembly, the crankshaft was polished to a near interference fit with the two ball bearings that would reside in the nose case. The first operation was to install the bearings into the nose case. This was accomplished by warming the nose case to 220 degrees Fahrenheit in the oven and chilling the bearings on dry ice to minus 190 degrees Fahrenheit. The bearings were done one at a time. Once the bearings were in place, the nose case was again heated to 220 degrees Fahrenheit, the crankshaft chilled on dry ice, and then the components rapidly and forcefully fitted together. These photos show the test assembly of the Bantam 3.5 without the crankcase. The right-hand photo shows a close-up of the rotary valve in place between the crankshaft cheek and the rear case. The original timer arm lever, shown on the left, proved problematic. It fit loose in the groove, and the screws used to attach it to the timer were quite loose in their threads. I made a replacement timer on the right, which was designed in shape and angle to limit the amount of movement of the timer lever from top dead center on to 30 degrees before top dead center for running. The left-hand panel shows the timer lever in place in its groove on the back of the rear cover. The right-hand panel shows the timer in place secured by 256 fiber nuts. You can see that by design, the travel of the lever arm is restricted by the aluminum engine bearers. Wiring the Bantam 3.5 is quite simple. Again, the timer simply acts as an on-off switch to fire the dual coil at the appropriate time. Setting the timing on the Bantam twin is quite straightforward. You set the crankshaft at near top dead center, and you adjust the points such that they just open as the pistons reach top dead center, thereby firing the plugs. The integrity of the ignition system is best checked with remote spark plugs so that you can verify that spark is being delivered to the spark plugs at the correct time. Without a reference manual or instructions to the engine, I chose a typical but conservative advance limit of 30 degrees before top dead center. Establishing the 30-degree range was done with a digital angle gauge that was hot glued to the timer. Knowing from the start that I wanted to run the engine, this would require having a propeller hub made as well as either a test club or a propeller. References state that the engine would turn a 20 by 18 propeller at 6,500 RPM, but I chose to go with a test club for safety and simplicity. A beautiful stainless steel hub was machined by H&K Precision Machining in Lake Barrington, Illinois. I cut my own test club from a 1-inch thick piece of carefully selected birch. It was 18 inches in diameter with a constant chord and a constant pitch across the span of the blade. The key is to make each station on one blade identical to the same station on the opposite blade, and that the blade be well balanced. I used a lawnmower blade bubble balancer to accomplish this. Here's the Bantam 3.5 ready for its first run. For fuel, I used 30% two-stroke oil in 70% Coleman stove fuel, which is white gas. I used a 6-volt 4.5 milliamp hour lead-acid battery with a 6-volt aftermarket dual coil typically used on a Honda motorcycle. Fuel tank came from a weed whacker. It uses vintage Champion V plugs. New piston rings were installed, and these were made by GC Rings in Bedfordshire, UK. The engine stand was made from scrap plywood that was epoxied and screwed together. The aluminum engine mount was 1/2-inch aluminum bar stock secured with expanding rubber well nuts to provide a modicum of vibration isolation. The back side of the blades had reflective tape to be better picked up by the laser tachometer. The first attempts to run the Bantam 3.5 were both a revelation and a disappointment. The engine would start, but only on prime, and it would run for only 1 or 2 seconds. After that 1 or 2 second run, the engine appeared to be flooded out, and this was confirmed by wet spark plugs. Our theory was that low airflow through the carb or an excess fuel head at the start may be delivering dribbling wet fuel and not atomized or vaporized fuel. We confirm the compression, timing, and spark plug were all correct. The second run attempt on the Bantam twin was successful. 3 changes were made, which included a choke sleeve to slide over the carburetor intake. This sleeve had 2 3mm ports in them, and the hope was that it would accelerate the airflow through the carburetor and perhaps induce some swirl. The fuel tank was lowered to prevent excess head, and the fuel was doped with a 4-second burst of starting fluid. This data table lists specific information collected during the run you just saw. Of note are the temperatures taken immediately after the run, showing that nearly 300 degrees Fahrenheit was observed at the base of the spark plug, while the rear case was only 150 degrees. Having the luxury of 4 engines to examine revealed a number of differences in various parts of the engine. I cannot say which parts belong to which era, meaning the 1940s versions or the 1960s. Here we can see 2 different styles of crankshaft webs, 2 different styles of crankcase castings. There were variations in where the spark plug hole was located, the size of the timers. Some of the small ends of the connecting rod were drilled, others were not. The drilled and undrilled variations on the rear cover, as well as the position and size of the carb securing screw. Here's a table showing the weights of the various components. I doubt anybody else will make a video on the Bantam 3.5, so I thought that I would include this information here. The 9 surviving Bantam twin engines known to me are shown on this slide. Only 2 of these engines are stamped with numbers on their crankcases, and it is unclear how to assign which era any of these engines may have been produced. The first 3 engines shown here can be viewed in the collection of the Miniature Engineering Craftsmanship Museum, and the rest are in private hands. I thank you for watching this video, and I can be found at doolittlefay@aol.com.